Welcome back to ECE 501B. In this video we want to talk about the singular value decomposition for a linear operator and then look at that actually for a more general case where we might not be worrying about a linear operator but a linear map. And we will start then with Theorem 51, which actually provides us with a singular value decomposition of a linear operator. We haven't yet really talked about that. We've talked about a polar decomposition and we have defined singular values. Now let's generalize that and talk about a way to factor a generic linear operator T. In this case, Theorem 51 says, suppose we have a linear operator T with the following singular values, S1 through Sn, and we know how to find those. Those are the non-negative square roots of the eigenvalues of T dagger T. We now have a linear operator T with singular values, n of those, so we're assuming V is an n-dimensional vector space. There exist two bases, E1 through En and F1 through Fn on this vector space V, such that we can decompose this operator operating on a generic vector V in the following way. We can take the first singular value, that's a scalar, that's a positive number, and scale it by the inner product of this arbitrary vector V with the first basis set vector E1, and that will give us a scalar, the inner product of V with E1. We form that product of S1 with this inner product, that's a scalar, and we use this scalar to weight this new basis vector F sub 1. So now we're basically saying, how does V align with the input vector basis E1, E2, En? That gives us scaling. We scale those by the singular values, and then we use those weightings to weight this second basis vectors, set of basis vectors, F1 through Fn. That is then defining singular value decomposition. Let's see how that could be shown. From the spectral theorem, we know that we can find this orthonormal basis E1 through En for a positive matrix, and we have a positive matrix from this square root of T dagger T. So once we have this positive matrix, we can find an orthonormal basis that actually consists of the eigenvectors, and we can then find the eigenvalue eigenvector decomposition of that positive matrix, square root of T dagger T. Once we have that, then we can say, once we have a basis, we can then use that basis to decompose any vector little v. So for any little vector v in our vector space V, we can write that vector v in its decomposed form. We can say, what's the component of v in the direction of E1, and use that to scale E1. What's the direct or the component of v in the direction of E sub 2, and use that to scale E sub 2. And we just continue to do that for all of our basis vectors, and so we now have this orthonormal decomposition of a generic vector v in our vector space. We can now actually apply the positive operator, square root of T dagger T, to both sides of this equation. And remember that these inner products produce a scalar. On the left, we then have the positive, or we have the square root of T dagger T applied to V, and that's now equal to Well, now if we apply the positive square root of t dagger t to these basis vectors, we've already defined what those look like. Those just give us this eigenvalue times the respective eigenvector e sub I. So if I now operate the square root of t dagger t on E1, remember the inner product of V with E1 is a scalar, so that now I can actually write that as S1 inner product of V E1 E1 plus S sub 2 V E2 E2, etc., all the way to S sub n V En times En. Let me call that equation star. That's an important equation that we will refer to later. So now we have weightings on this orthonormal basis, E1 through E sub n, and those weightings involve singular values of our operator t, which are the eigenvalues of this square root of t dagger t. We also know that we can decompose our operator t into its polar decomposition. And we have seen that there is an isometry S on our linear vector space V such that t is equal to S square root of t dagger t. That's from our polar decomposition result. Once we have that, now we can apply our rotation, this isometry, to both sides of equation star. So now let's apply this isometry S to each side of equation star. So that now on the left we have S operating on the square root of t dagger t applied to V, and that's now equal to S times S1 inner product of V1 E1 E1 plus S sub 2 inner product V E2 E2 plus plus S sub n inner product of V e to the n e to the n. And realize that this is in fact how we decomposed our original operator t. We can see that all of this in each of these pieces is just a scalar, so it can be factored through or pulled outside of S, and we now have S operating on E1, we have S operating on E2, we have S operating on the vector E sub n. We can now use that to select a new basis. S, remember, is simply a rotation, and E1, E2, En is an orthonormal basis. If we apply an isometry to an orthonormal basis, we get an orthonormal basis back. That means that we can now choose a new orthonormal basis, F1, F2, Fn, such that S applied to each of these original, let's say, input basis vectors E sub I is equal to F sub I for all I equal 1, 2, up to n. That means then that this equation tells us that we have TV on the left is equal to, sliding S through on each of these coefficients, we have S1 inner product of V1 E1 times SE1, but we're just defining SE1 to be F1. Or we now have S1 inner product of VE1 times F1 plus S2 inner product of V with E2 times capital SE1, capital SE2, which is just F sub 2, and we can simply keep going, plus S to the n times the inner product of V with E to the n times capital S E to the n, but that we've defined to be a new basis vector F to the n, and that's actually what we set out to prove. We've now established a singular value decomposition of a generic operator T. Granted, it now has two orthonormal basis vectors that are associated with that general operator, linear operator T. That's very powerful, and it's almost impossible to say too much about this singular value decomposition. One is it shows action of any operator, which we've been calling T, can be written as a decomposition in one basis. That's the V E sub i's. Then we actually scale that projection onto each of those input vector spaces, E sub I, scaling of each component by the appropriate singular value, which we now are labeling S sub i's, and then redirecting those based on the F sub i's, or a recomposition in a different basis of F sub i's. We figure out how V is decomposed into the E, the input basis. Then we scale those scalings, and finally we use that product of scalings to adjust or scale the output orthonormal basis F sub i's. And that's actually a little bit different than what we've been used to. That's a little bit weird because now we have two orthonormal bases. And in general, or normally, we normally only use one basis when we're dealing with an operator. Here we have two bases. We have an input basis, those were the E's, E sub i's, and an output basis. And just like with a matrix representation of a linear map, we can now think about using that in this particular operator. We can say, well, what does the matrix representation of this linear operator T look like when we have an input basis of E's and we have an output basis of F's? What does that matrix representation actually look like? In fact, that gets us back to a nice matrix representation. It actually produces a diagonal matrix with the singular values on the diagonal of that matrix, where our input basis are the E's and the output basis are the F's. Meaning we take a generic vector V, we decompose it in the directions of our input basis vectors, E1 through E sub n, by forming these inner products. We scale those with the singular values, and then we use those weightings to weight our output vectors F1 through F sub n. And in fact, even though this might be a little bit weird, now we can extend this operator singular value decomposition to a linear map. In fact, we can apply the singular value decomposition to generic linear maps, where those linear maps now are between, let's say, unequal vector spaces in terms of dimension. V might be n-dimensional, as in Nevada, and W might be m-dimensional, as in Michigan. So that now we have a way of generalizing of our eigenanalysis, eigenvalue, eigenvector, to rectangular matrices using these singular value decompositions. We now have a generalization of eigenanalysis to linear maps or rectangular matrices if we were interested in their matrix representation versus square matrices. And I hope that you realize that a rectangular matrix or a rectangular linear map doesn't have eigenvalues. No eigenvalues exist for a generic map, but in fact, going through these singular values, which require the eigenvalues of a positive matrix, that positive matrix, this square root of t dagger t, is in fact square by construction. So this positive map or operator in this case, it does have eigenvalues, and those are what we use as the singular values of the linear map T. And that allows us to view this singular value decomposition in a matrix form, or as a matrix factorization, where if we allow T now to be a matrix, I'm abusing notation a little bit, we now have U, because we typically use T to represent a linear map, but now we're going to write T, a matrix, as U sigma V transpose. And that can be done very cleanly in MATLAB with one command. If we simply say the output of our command in MATLAB is going to produce three objects. The first one is our U matrix, which I'm using as a lowercase u. The middle object is our singular values S, and the third object V is a matrix V. That will be found by simply typing SVD applied to some map T. I've actually done that here for a particular matrix A. Maybe I should go and show you what I have now done in MATLAB. Here is an A matrix that's no longer square, it's rectangular. It has 3 rows and 4 columns, and we want to now find the singular value decomposition of that matrix. So here's our A matrix. We can actually find its transpose by simply making the first row the first column, the second row the second column, the third row the third column. There's our A transpose. And A now has as its domain, what are the input vectors going to look like, where they have to be compatible with A. A has 4 columns, so if we hit that A matrix or apply that to a vector, the vector that we apply it to has to be 4-dimensional. The domain of A is then R4. Those are our inputs. That produces a 3-vector. Our codomain then is living in R3, and those are our outputs. To actually do the singular value decomposition, or what does the singular value decomposition produce, we're now decomposing this matrix, a rectangular matrix, into a product of 3 other matrices. 2 of those 3 pieces are actually basis vectors. They're orthonormal vectors. We have orthonormal vectors in U. We have orthonormal vectors in V. Sigma is a very nice matrix. It's actually a diagonal matrix, or has only non-zero entries on the diagonal, and some of those could be 0, but sigma is a diagonal matrix that doesn't have to be square. What does that mean? Well, A in our example was in or associated with a 3x4 matrix. That means this decomposition has to be compatible with A. In order to be compatible with A, what does U have to be? Well, we know that U needs to be compatible with A, and U tells us the output dimension. We have 3 rows in A, so U has to have 3 rows, but we said it was orthonormal vectors, so U has to be square, and it needs to be 3x3. Likewise, V has to be consistent with A, and V then has to have the same number of columns as A has. And A had 4 columns. V is orthonormal vector, so we know it's square. If it had now 4 columns, it also has 4 rows. V is now 4 by 4. Sigma is our diagonal matrix. It's now sandwiched between U and V. It has to be mathematically or matrix-wise compatible or consistent with U and V, so it now has to map a 4 vector into a 3 vector, meaning sigma is now a 3 by 4 matrix. It's rectangular and it has only non-negative entries along the diagonal. Now recall that the positive square roots of the operator t dagger t are the singular values of t. So if we can now find the eigenvalues of A transpose A, which we can do because it will be a square matrix, we will then be able to find the singular values of our original operator t. Doing that for this particular case, I'm not going to walk through that, but A dagger A is the same or equal to A transpose A. That gives us now a 4 by 4 matrix. It's square. We can now compute the eigenvalues of that square matrix. The eigenvalues become 3, 9, 0, and 0. And from this top line, we say, oh, we need to take the square root of those 4 non-negative numbers to find the singular values of our original operator t. The square root of 3 is one of our singular values. The square root of 9, which is 3, is another, and we have 2 singular values that are 0. Our singular values of A then are 3 from largest to smallest, square root of 3, 0, and 0. We can now use that to create this 3 by 4 rectangular matrix that's diagonal, putting the largest singular value first and then descending in size in singular values along the diagonal. Here is our diagonal, and we need to now pad zeros onto that diagonal, those diagonal entries, in order to find or to produce the sigma having the correct dimensionality, which we know it needs to have 3 rows and 4 columns. It could have been, for another case, maybe 5 rows and 3 columns, and we would have to pad zeros in the appropriate direction, either in columns or in rows. Here we had to append an additional column of zeros. We can now partition this this rectangular matrix sigma into one submatrix that has non-zero entries. That's 2 by 2, and that's what we're now calling sigma bar, and all the other submatrices of the appropriate or compatible dimensions are 0. In sigma, we have a 3 by 4 matrix. We only have a certain submatrix within that rectangular matrix that has non-zero entries on the diagonal, and that's what we're defining to be sigma bar. And that's now this 2 by 2 matrix consisting of 3 and square root of 3 on the diagonal. If we now looked at what MATLAB produces, I've now typed these in so that you can read it. I didn't want to write all of those 4 significant figures in my own handwriting. Here hopefully you can see. But now what we want to do is actually compatibly dimension or partition U and V with sigma. We know that U, sigma V transpose, makes up A, but now we have a particular way of breaking up sigma into parts. We've now dimensioned it or decomposed it to have a 2 by 2 in the upper left hand corner, a 1 by 2 in the lower left corner, a 2 by 2 in the upper right, and a 1 by 2 in the lower right. We want to compatibly partition U and V. Doing that now says that we actually need, in terms of U, remember that U now is an orthonormal basis, and two of those vectors are going to get scaled by 3 and the square root of 3 when we multiply it by sigma. The remaining vector, in this case we just have 1, we will call U sub 2. And now we can actually find what those look like in terms of their dimensions. U1 has 3 rows and it has 2 columns, and that's compatible with how sigma, the rectangular matrix, is partitioned. U sub 2 has 3 rows and 1 column. But what can we also say, since we know that A is equal to U sigma V transpose? Whatever we can get to when we map through A, we have to be mapping through U. Or, what is U2 weighted by? U2 is weighted by 0, so the only thing that's going to give us things in the range of A are columns in U1, or the span of the columns in U1. Writing that down then, the span of U1 is going to be consistent with the span of A, which is actually the range of A in our notation that we've been using throughout this course. But what else do we have? Well, we also have U sub 2, which is a basis vector in this vector space that's R3. And it's now U, the vectors in capital U form an orthonormal basis. So the column U sub 2, or the columns in U sub 2, in general it will have multiple columns. The columns in U sub 2 are orthogonal to the columns in U1. So we now have a way of orthogonally decomposing that vector space 3 by 3 vector space. Or we can now say that the span of U sub 2, what does it span? Well, it actually now spans the orthogonal complement of the range of A. Since the range of A is a 3 space in this example, and we only have a 2-dimensional range of A, then the orthogonal complement of A is actually going to be spanned by U sub 2, the columns in U sub 2. We can do something similar relative to V. So V now needs to be compatible with sigma. In this case, we see that we have now V1 and V sub 2 relative to the decomposition or the compatibility of V with sigma. And what are the dimensions? We can now say that V1 is 4 by 2 and V sub 2 in this particular example is also 4 by 2. And what are some observations that we can make? Maybe this will help with your understanding of what we're doing in terms of partitioning and making U1, U2, V1, and V2 definitions. U and V are created as, or built from, orthonormal basis. That says that if we take U and multiply it by U transpose, we end up with the identity, which in this example is 3 by 3. If we take V and pre-multiply by V transpose, it's now 4 by 4. So now let's look at what we have when we have A, which is U sigma V transpose, written in this decomposed manner of U1, U2, sigma bar 0, 0, 0, and V1, V2 transpose. So what happens if we apply the matrix V to both sides of this equation? Well, on the right, we end up with V transpose V, which is the identity map. Or if we now said that we have AV, that's now A times V1, V2, but that's simply U1, U2 times this rectangular matrix of singular values, because the V transpose V is the identity map. And what do we have on the right-hand side? We now have U1 times sigma bar plus U sub 2 times 0. And in the second partitioned space, we have U1 0 plus U sub 2 0, performing this submatrix structure. Or if we now put those pieces together, we have A V1, A V2, distributing A through the columns in V, and on the right we have U1 sigma bar, that's our only non-zero component, and 0. Well, what can we back out of this dimensionally? How many rows did we have in U1? U1 actually possessed, or U2 possessed 3 rows. How many columns were in U1 or in sigma bar? Sigma bar had 2 columns associated with it. And how many columns did we have here? We had 2, so this now gives us 2 columns, and there is a 3 by 4 matrix on the right. That has to be partitioned compatibly with what's on the left. So now we can see that V2 consisted of 2 columns, so that AV2 is 2 columns wide, and AV1 is 2 columns wide. What does that tell us? Well, now we can say that AV1 is U1 sigma bar, which lives in a 3 by 2 space, and AV2, which is now 0, lives in a 3 by 2 space. But what does that mean about the vectors V2? These are non-zero vectors. V2 completed the R4 orthonormal basis. We can now say that the span of V2, all columns in V2 map to the 0 vector, so these actually give us the span of V2 correspond to the null space of A. And remember, the columns of V form an orthonormal basis, and we've already found that one of these orthogonal decomposed partitions of V1 and V2, the V2 set spans the null space of A, V1 is orthogonal to that, which says then that the span of V1 must be the orthogonal complement of the null space of A. We now have basis vectors for the null space of A and its orthogonal complement from the columns in V. And before, didn't we had a span of U1 corresponding to the range of A and the span of U2 corresponding to its orthogonal complement. And those are actually our four fundamental subspaces associated with any operator T. Therefore, in general, these basis vectors coming to us from this singular value decomposition of a generic matrix T, which we've now defined as U and V, where A is equal to U sigma V transpose. These basis vectors, they're not the same in general. We have basis vectors in U and we have basis vectors in V. They may not even be of the same dimension if our A matrix is rectangular. These provide orthonormal basis for the four fundamental subspaces of a generic matrix. In our example, our matrix was 3 by 4. And those four subspaces, if you now find the singular value decomposition of a general linear matrix, linear map A, then we can find a basis for the range of A. That's just going to be, we've identified the columns in the U matrix corresponding to the non-singular or the non-zero singular values, and that then gives us the span of U1. The orthogonal complement to the range of A is what completes that basis, so the span of U sub 2 spans the orthogonal complement of the range of A. Likewise, the null space of A was spanned by the columns in V sub 2, and since the columns in the matrix V were an orthonormal basis, we now have a way of creating basis vectors that span the orthogonal complement to the null space of A, and those are the columns in V1, or that's then equal to the span of V1. I really can't emphasize enough the significance of this singular value decomposition. A matrix A is equal to U sigma V transpose. That can be computed in MATLAB, generating the U matrix, the singular values. Here it was 3 and the square root of 3, and our two matrices consisting of orthonormal bases U and V. Those matrices U and V can now be compatibly decomposed into U1, U2, V2, and V1 to create basis vectors for the four fundamental subspaces associated with a generic matrix A. If our matrix A is injective, we have a trivial null space, then V sub 2 will not exist. All the columns in V will correspond to the columns in V1. If our map A is surjective, then we won't have an orthogonal complement to the range of A, and all columns in U will be obtained in U sub 1, and U sub 2 will not exist. Hopefully that is clear, and you now have a way of producing or finding the four fundamental subspaces of any general map A through the singular value decomposition.